This is the video for accelerated geometry on section 11-3 on investigating graphs of polynomial functions. Key vocabulary in this video will be end behavior, turning point, local maximum, and local minimum. The essential question we will be answering is how do you use properties of end behavior to analyze, describe, and graph polynomial functions? The end behavior is a description of the values of the function as x approaches infinity or negative infinity. So this little chart that you have in your notes here is just a little key that can kind of help you remember which is which. So first thing you want to look at is, are you looking at an odd degree function or an even degree function? And then the next thing you want to do is look at your leading coefficient. If your leading coefficient is greater than 0, which means it's going to be a positive leading coefficient, then you're going to follow this row. If your leading coefficient is less than 0, which means that it's a negative, then you're going to follow this row. So our end behavior, you're going to have one of four options. It's either going to be this one, because it's an odd degree with a positive leading coefficient, an even degree with a positive leading coefficient, a odd degree with a negative leading coefficient, or a even degree with a negative leading coefficient. So in our first set of examples, it says identify the leading coefficient, degree, and then write the end behavior. So if I look at this, my leading coefficient would be 2. My degree on this one is 5. So ultimately what I'm doing here is I notice that I have a positive leading coefficient and an odd degree. So if you refer back to your chart, and what I would do is pause the video for a second and flip your page and look at the chart, and you will see that in the box that is for a positive leading coefficient and an odd degree, which is the box on the top left there, that your end behavior is going to be as x approaches the positive infinity, the right side, your function approaches positive infinity because it goes up. And as x approaches the left, the negative infinity, your function approaches negative infinity, which means it's going down. Ultimately, whatever happens in the middle, we're not really concerned with end behavior, but in the end, your graph is going to take on something where the left is pointing down and the right is pointing up. Whatever happens here, we're not concerned with end behavior. Let's try another one. So our leading coefficient is -3, and our degree is 2. So ultimately, we have a negative leading coefficient and a even degree. So again, pause the video, look at your chart, find the box that's labeled for a negative leading coefficient and even degree, which would be the bottom right-hand box. So we know our graph is going to ultimately do something like this as far as the ends are concerned. Whatever happens in the middle, we're not worried about. So I know that my end behavior is going to be as x goes to the right, the function, which in this case is s, of x is going down. And as the function, I'm sorry, I said the right here, so that would be a positive. And as it goes to the left, the function is also going down. The next set of examples says to identify whether the function graph has an odd or even degree and whether it's a positive or negative leading coefficient. So ultimately what I'm doing here is I'm just looking at the ends. So ultimately I have going up on the left and going down on the right here. So which graph from the chart is going up on the left and down on the right? And if you look at your chart, that looks to be the bottom left-hand corner. So that tells me that this function has to have a negative leading coefficient and an odd degree. On example 4, again, we're only concerned with the ends. So in this case, it looks like they're both pointing up. So we're going to look at our chart and find the one that they're both pointing up, and you will notice that that corresponds to the one that is in the top right-hand corner. So that tells me that this is a positive leading coefficient and an even degree. The definition of a turning point is a point on a graph at which a function changes from increasing to decreasing or from decreasing to increasing. The graph of a polynomial function with a degree of n has at most n minus 1 points, turning points. So for example, if you have something with the highest degree, say we're looking at an x cubed, your degree here would be 3. So what this is saying is there are at most 3 minus 1, which would be 2. So at most 2 turning points. A local maximum or minimum is the y-coordinate of a turning point. So the maximum changes from increasing to decreasing, and a minimum changes from decreasing to increasing. Okay. Next, what I want you to do is to pause this video, and I want you to go through these steps that I have here for this example that's worked out so that you know whether or not you know how to use your calculator. We will go over some of this in class tomorrow as well. Okay, so what I want you to do is to go to y equals and type in this function. And then I want you to find the maximum according to these directions and find the minimum according to these directions. Now, just to be clear here, when you're finding your maximum, you have a marker. It kind of looks like a little X that's flashing, and on your screen, it will say left bound. And what that means is if this is your maximum, you want to make sure that that cursor is to the left of that point. And then it will ask you for a right bound, so you want to make sure that it's somewhere over here to the right of that point. Even and odd functions. Algebraically, what should happen if you have an even function is if you plug in negative x, you should get out a positive x, like the same function you started with. If you plug in for an odd function, if you plug in negative x, you should end up with the opposite of whatever your thing was. However, there's an easier way of thinking about this, which I'll show you in just the example. I'll show you both of these. And then graphically, you're going to be asked to describe the symmetry. So if you have an even function, you're going to say that it's symmetric about the y-axis. And if you have an odd function, you're going to say that it's symmetric about the origin. Okay? So first things first, using the algebraic definition, what this is saying is if I plug in f of negative x, I'm going to have negative x to the fifth minus 5 times negative x to the third plus 3 times negative x. So if I look at this, a negative to an odd power is just going to be negative. A negative to an odd is a negative times a negative would be a positive. And then a positive times a negative would be a negative. So comparing these two functions, is it the exact same function that I started with? No. Therefore, it's not even. Is it the complete opposite as far as the signs are concerned from it? Where I had a positive, now I have a negative, I have a positive, I have a negative? The answer to that is yes. So that makes this an odd function. The other way to look at this is if you just look at the degrees of each term. You have a degree of 5, a degree of 3, and a degree of 1. So 5 is odd, 3 is odd, 1 is odd. Therefore, it's an odd function. So the answer to the second part would be, since it's odd, we know that it's symmetric about the origin. Let's try another. If I use the algebraic definition, you'd have f of negative x equals negative 2 times negative x to the third plus 3 times negative x squared. A negative to the third is going to be a negative, so a negative times a negative is a positive. A negative to an even power is a positive, so then that's just going to be plus 3x. So we ended up with an opposite sign here and a same sign here. So they're not all opposite and they're not all the same as the original function. So this one would be that it's not odd and it's not even. If you look at your degrees, you have an odd degree and an even degree. So since it's a mixture, it can't be an odd or an even function. Number 7, if I do it algebraically, you would have f of negative x. It's 5 times negative x to the 6th minus 3 times negative x squared plus 4. So a negative to an even degree is a positive, so that's going to be 5x to the 6th. That's going to be a positive times a negative would be a negative 3x squared, and then plus 4. And if you notice, I ended up with the same exact function that I started with, so that's going to be an even function. And if you look at your degrees, 6 is even, 2 is even, and again, a constant you can think of as something to the 0th power there. So that's even as well. And we would say that it is symmetric about the y-axis. Okay, let's put all of this together. First thing I would do is get your graphing calculator and type in your function of f of x equals x to the third minus 2x minus 3 into y equals. Your graph should look like something that I have right here. That's the first thing I would do on these problems, is always start with graphing it in your calculator. The next thing I would do is I'm going to find my maximums and my minimums. So I'm going to use those directions from earlier, and I'm going to calculate this point right here. And when I do that, I get that this point is at, I'm just going to put it off the side so you can read it, negative 0.8, negative 1.9. And then this point down here is at 0.8, negative 4.1. And then I'm also going to calculate the 0, and so it crosses at that's 1.90. And so now I can answer any question that comes up. Okay, so from the beginning, the degree is 3. the leading coefficient is 1. Domain, am I restricted on x values? No, so the domain is all real numbers. Your range, if you look at your graph, does it cut off on your y values or does it go all the way up and all the way down? So in this case, we're not restricted on anything. So my range is also all real numbers. Even, odd, or neither. We have a degree of 3, a degree of 1, a degree of 0. So since it's a mixture of even and odd, it would be neither, which means there are no symmetries. For intervals of increase and decrease, what I like to do is kind of draw a number line and then put in your maximums and your minimums. So if you look, you start over here at like negative infinity. Then your next point here, the x coordinate of that maximum was negative 0.8. The next one is positive 0.8. And then it looks like it keeps going on towards positive infinity. And then if I look at this, again, we're going to read it left to right. So left to right, we go up. So that means it's increasing. Then we go down. So it's decreasing. And then we go back up. So it's increasing. And then you have your intervals for your increase and decrease. So we start off with saying from negative infinity to negative 0.8, it's increasing. Then between these two values, it's decreasing. So from negative 0.8 to 0.8, it's decreasing. And then it increases again. So we have from 0.8 to infinity, it increases. In behavior, on the right side, it's pointing up. And on the left side, it's pointing down. Evaluate f of x for x equals negative 3. You can do one of two things. You can use synthetic division for that. You can use direct substitution for that. Or if you have your graphing calculator, you can hit your second graph button, which brings up your table of values, and find out that at x equals negative 3, y is negative 24. For your minimums and maximums, you already have that answer here. So there is a minimum, your bottom point here, at 0.8, negative 4.1, but by the definition, it is the y coordinate. So I would also take or y equals negative 4.1. For your maximum, it's this high point, so that was at negative 0.8, negative 1.9, or you could put y equals negative 1.9. Now, what I would like you to do is to pause the video and try this example from beginning to end for yourself, and then come back to it to see if you did it correctly. So first step is typing the function into y equals into your calculator. And when you do that, your graph should end up looking like this. Next, I like to calculate all the maximums and minimums. So if we look, we only have one minimum, which is right here. And when you calculate that, it comes out to be 0, negative 6. If you calculate your zeros, it crosses the x-axis at 1.1. And negative 1.1. So go ahead and answer our minimum question here. We could have 0, negative 6, or y equals negative 6. Maximums, there are none, so just write none. If I scroll up, the degree is a 4. Leading coefficient is 1. Domain, if you look at your graph, you're not restricted to your y values. your x values. So your domain is all real numbers. Your range, however, if you notice, the graph never goes below this point. So your range is restricted, and the y-coordinate at that point is -6. And if you notice, all the points are above it. So our range is going to be all real numbers greater than or equal to -6. Is it even, odd, or neither? You have a positive, an even, and that's really a 0 there. So that's also even. So this is going to be an even function, which means for your symmetry, you're going to have that it's symmetric about the y-axis. For our increase and decrease, again, if I make a number line, we only had that one minimum at 0. So we have -infinity on the left and +infinity on the right. So if I read my graph going left to right, we go down first. So that means this decreases. And then we go up. So this increases. So my intervals of increase would be from 0 to infinity. And my intervals of decrease would be from -infinity to 0. In behavior, it looks like they're both pointing up, so these are both going to be positive infinities. And if I use my table of values and find when x is -3, we get 111.